So let's start. So as we discussed the last session from this week, we'll take a look at the chapter 27, DC and the circuit analysis. So the circuit analysis based on the DC circuit, not AC circuit. So DC and AC is slightly different. The basic concept is the same, but DC based on the static, potential bias. So their plus and minus bias is not changing in time. So once the wire in circuitry actually bias with the one potential, like positive and negative, they're static. They don't change. Just stay with the same quality of electric current. So for this chapter 27, all the way down to the maybe magnetism, we'll stay with the DC circuit analysis too. So let's take a look at the first concept of DC circuit analysis, which is the voltage and current. They are the basic kind of tool to analyze the circuit model. So if you look back, if you just refresh your memory and think about the energy out of the gravitational force, if you have a change of your position relative to the reference point, you should be able to create this amount of energy based on the change of your position. So that is gravitational potential energy. So now you're assuming you bring the water from the surface of ground to maybe like 10 meters away from the ground, and that has some container. You can think of this as dam, and that H is about 10 meters. Then you open the gate of the dam, then water flows down to the reference surface. So that flow of water is created by the difference between those two spots. The reference point H, the y equals 0, and the y equals 10 meters. So that difference of your relative position created some amount of work that produce amount of energy. So that make the water flows from the higher spot to the lower spot. That water flower produce the energy. So difference of these two, the spot could be difference of y that produce the potential energy that create the water flow. That kind of image, you can actually project the same kind of image onto the electric circuitry. So if you have some sort of like electrical wire, but they are disconnected, they're discontinuity, and they're biased with a different amount of potential. So let's say this is 0 volt, and you have 10 volt, the other side of the wire, then you are instantaneously to connect them. Then that difference between those two electric wires produce that the amount of current flow from higher potential bias down to the lower potential bias electrodes. So that current of electric charge flows from the higher potential onto the lower potential. So that difference between these two electrodes has amount of energy. It's the same as the gravitational potential energy, but that's called the electrical potential energy. So now current flow out of these two electrodes, that is maybe this one is B1 and this is B2, and delta B is B1 minus B2. So that whatever number of the potential bias apply to the two different electrodes that produce the potential difference that should create the amount of the current flow from higher voltage to the lower voltage. So the current flow over time is proportional to the amount of charge going through that cross section of the wire. If you think of this cross section as delta A, and this amount of charge delta Q passing through this cross sectional area within delta T time interval delta T, that is normally called the current. So current basically is defined by finite number of the charge travel along the cross section in unit time, travel time. So you have more time you monitored in the given area of wire, it should create the more current. I mean, it should actually, you will see the more current, I mean, more charge and passing through this cross-sectional area. So basically the current itself, the ratio of the charge moving along the cross-sectional of the wire in given time. So there here delta Q would be Q2 minus Q1 over T2 minus T1. It's just like same as the velocity concept, but that's obviously they're different physical quantity, but the way of defining this average current is same as the velocity out of displacement in given time. So if you have energy source, which is battery connected to the electrical wire. So I'm just giving you a very, very elementary model of the circuit with the basic element. So now you have wire with the resistor, which has intrinsic resistance R. If you just leave the wire without any energy source, there's no, nothing happened because there's no potential difference applied to the one side of the wire and the other side too. So, but if you connect this two ends of the wire terminal with the battery, then that creates the potential difference between upstream of the wire to downstream of the wire to produce the current flow, and that's as goes through this resistor with the current I. So that battery cell have this amount of potential difference, then your total amount of potential difference is basically the amount of work produced by the current divided by unit charge, or the charge that passing through this wire. So there are two ways to analyze the amount of work created by this battery. Once you plug that battery into the wire in the closed loop, that should produce the current flow, while this current going around this closed loop, that should produce the same amount of work. So there are two different ways to estimate this or analyze this circuit. Number one is energy method. The second one is potential method. So let me give you the first method, energy method. So whatever amount of the work done in the system should be same as the amount of energy produced by this battery or electrical source. So that energy method is based on the energy conservation. So total amount work produced by the amount of work produced by this battery is potential difference times dq based on this definition. And now this is potential difference dq could be redefined with this definition of current. So the current itself, if you define the instantaneous currents by the differentiation of the charge in time, that should be dq over dt. So that could be dq is the constant current times the unit time. So if you replace dq with the I dt, then that should be I dt. So not this one. So Ohm's law, I don't know if you learned that the Ohm's law yet, but basically the voltage difference is the I current times of resistance. Okay, that's basic Ohm's law. So if you replace it, then that should be IR times I dt. So that could be I square R dt. So basically from that, from this one, you could actually drive that this relationship too. So I amount of current is the potential difference created by the battery divided by given intrinsic actually resistance. And that is the basic relationship of the resistor and the current and the voltage difference by the battery, that based on the energy conservation. And the second way to analyze this closed loop of unit model is potential method. I'm just giving you a basic method to analyze the simplistic circuit model. So the potential method is now, if you pick up the 1 point out of this closed loop, and if you're going along this closed loop, and the resistor normally produce the potential drop. So when current going through this resistor, then that has the potential is just lower. And once this current comes back to this battery, then actually just increase that potential. As long as you're going along the positive direction from the negative bias to the positive bias. So loop, closed loop is same as current flow, then you have gained the energy, but resistor actually lowered the potential. So whatever just the loop you're going through, once you come back from starting point like this, then total potential increase and total potential decrease should be equal. So there's no net actually potential change. So with that idea, if you think of there's some kind of imaginary potential existing there, then potential created by this current at point A plus, now because you are going along the same direction of the current, you have the amount of potential produced by the battery, but once that current goes through this resistor, then the resistor itself just knock down your potential. That's nature of a resistor, because that's actually kind of a frictional nature to prevent current actually flows. So that actually lowered the potential. So you have to bring that negative sign, the minus sign with that resistor. So you have like amount of potential increase by the battery, some amount of potential drop from the resistor. And once you come back to your spot again, that total amount of potential should be same as before. So from that, there is zero potential out of it, then that lead to the V of IR equals 0. So here, that same as epsilon is the IR current times the resistor. So one minor just notice this the EMP, like electromagnetic force itself is also same as voltage V. There's no difference. Only like expression of the symbol of the potential difference is sometimes used as epsilon, but many cases also use the V. So they are actually same. But as I said, that's V should be IR, or epsilon is IL2 for Bayesian model of circuit, DC circuit. Let's take a look at the more complex actually case. Let me move on to the next page. So now, yeah.
For the E, in the last slide, you said like E is equal to V.
Mhm.
So why can't, because I know like traditionally, like we learned about capacitors in the last unit,
Mhm.
and capacitors for the electric potential, like delta electric potential, we just use V.
Mhm.
So why now with
Delta
this,
V, right?
sorry?
Yeah, V. Yes, yes, yeah, V.
Yeah.
Right.
So now with resistors, why do we like change V into E? Like why do we change notation all of a sudden?
Uh, so traditional way to define the V is already assume that the capacitor itself is charged by the external energy source. Okay, so that we already assume that there's like some kind of current that produced at the minus or plus charge on the capacitor, but that is some sort of like what can I say? Like unknown energy source already existing in the given system. But this circuit, you have to actually introduce that the real energy source in the given closed circuit. So that's a different. So basically, this notation itself sometimes indicating that the battery, if you want to emphasize that the battery is produced the potential difference, then sometimes use symbol E or epsilon, but you can replace it with a V too. But the V is more kind of common terminology, more widely used to define potential difference. Whether you are just you have like already existing energy source to define the potential difference for capacitor or battery. Okay, doesn't matter. But the many cases, if you want to express, there's some kind of existing energy source which is battery in the given closed circuitry, then many cases use epsilon because that is more like a pinpoint and more like precisely describe this, a condition of the circuit with the battery. But you can use it like a V too. But
Okay.
that more common case, I mean, you use that the V if there's any type of potential difference of two electrode. Okay, it could be the capacitor, could be maybe like a battery or something. Anything produced that the potential difference, you normally use the V. But if you want to just maybe like more precisely actually indicate that potential difference produced by the energy source, especially like a battery, then many cases use the epsilon. Does it make sense?
Yeah, that makes sense.
So let me give you another common example so you can have a better understanding. So we will actually revisit some basic rule for analyzing the circuit with a different element, but I want to give you some basic idea. So if you have, for example, like a battery, as I said, and you have like a resistor like this. Now you're starting from maybe point A somewhere here, and now your point B is right there, and you want to just find out the potential, the distribution of your potential difference along the circuit element, which is battery resistor 1, resistor 2, and back to the battery. So in that case, you can actually just break that the point A or B and just spread them into the one-dimensional configuration. So now if you just break the A, let's just assume that you break the point A of a closed loop. This is epsilon, and you break the point A and then just rearrange it, this circuit in the one-dimensional configuration and put them in the one dimension. So like now you have point starting from the point A, goes to the battery first. You see that we're going through this clockwise the loop, okay? So you go through the battery first, and you move to the now register 1 R1, and you go to point B, you go to the register 2, and you're back to the point A. So you're starting from point A. Oh, so you already point A right there. And then you move to the point A along this circuit element is battery, resistor R1 and resistor R2, and this point B. So if you actually just move along with this circuit element and find out how potential difference varies along with this circuit element, then it would be like this. So this is the potential, absolute potential produced by the battery. So that is V, unit of V. So let me change the color a little bit. So now you're starting from maybe assuming you have some arbitrary potential VA. Could be 0 too. I mean, if your circuit is actually grounded, then the point A reference point could be defined by the 0 potential, like a 0 volt. But you can just put some sort of arbitrary number. So let's assume that this reference point of VA. You start a VA, and once you meet the battery, and the battery raise the potential up to some point much just higher, just raise up with the amount of the potential that the battery can create. So that might be the epsilon or V, doesn't matter, epsilon. Then that's now the battery just raise up the level of potential to the epsilon. And now just current goes through the next circuit element, R1, that is the resistor. As I said, if your current flow is the same direction of the loop, closed loop, then that resistor itself is supposed to knock down the potential with the amount of that their potential, internal potential. That should be maybe that amount of difference is Ri times R1, because now you only have one loop, one pass of the closed loop. So one current going through this one loop of the closed pass. So now that is I times R1 amount of the potential drops from the epsilon, and now you just move to the base point B and also meet the R2, the second the resistor. Then that might also knock down the potential to the VA while it's going down to, I mean, coming along that this resistor. So let me rewrite it. Okay, so that it should be knock it down the R2, the resistor. So you start with the VA, and that is the difference between this one is IR2. So that's VA. So that's what I already show you, that potential method. You start with the VA, and when you actually come along with the battery, then that produces that the amount of potential increase. And now we're going through the R1, the resistor, then is lower the potential. So you got to add the negative sign, minus sign in front of this resistor term. And now it's also going through the second register that also lowered your potential. So that's produced that the also amount of potential decrease. So you take that into account. You start from here, then end up with that, and that's create total net amount of potential change from epsilon to the IR1 and IR2. So that is epsilon is IR1 plus IR2. So amount of a potential increase is equivalent to the amount of a potential drop by two resistors. So total amount of actually potential change is just conserved, should be conserved. So that is the simple configuration of how to analyze that the closed loop of circuit, simple with a simple circuit element. When you have actually multiple paths of a circuit or current flow, and you may have, applied more complicating rules to analyze the circuit, but we will just, take a look at it shortly. But that's, I'm showing you how to just go through that, the basic circuit model with the basic concept. So far, do you have any question?
No, it makes sense.
Okay. So, oh, by the way, did your school already started this topic yet?
Our school does it weird where we learn about capacitance or capacitors before we learn about resistors.
Okay.
So, I just had a test actually today about capacitors.
Mhm.
So capacitors is all about like C is equal to
Yeah.
all that. Like we learned that, but we didn't learn about like resistors yet.
You know that this is actually perfect because you already learned the basic concept of capacitor, and now you're going into a resistor. But after that, we'll start to learn this circuit analysis. So you already have pre-study about this concept that definitely help you to catch the more idea of how this circuit analysis work. Okay. So let's move on. Then, as I said, if there's a multiple circuit element like a capacitor, resistor, put together into the one closed circuit, and you have to find how to analyze them in given condition, right? So I will show you how to do it. So first of all, in the case that there are multiple resistors plugged together in one closed loop in series, and then you want to find out what would be the total resistor in given system, right? So let me just show you the example. So now let's assume you have three resistors connected to the one single closed loop with the one battery. Now we have battery connected to the closed loop. You have one resistor, second resistor, and third resistor. So that is R1, R2, and R3. And as I said, you can just pick up the 2 point as a reference, A and B. And now you can naturally assume there's only one current path because there's only one wire connected from plus side of the battery to the minus side of the battery. So there's only one current going through the three resistor 1, 2, and 3. So there's three current flowers, but in the same direction. So number one, as I mentioned, based on the analysis I already show you, the amount of the potential increase should be same as amount of a potential drop produced by each resistors. So that should be IR1, IR2 minus IR3 equals 0. So based on that, your total current going through this single wire should be combination of three resistor, which is total potential difference divided by R1 plus R2 plus R3. And that is same as also if there's like one gigantic register representing this 3 register, then you can think of like there's only one equivalent register attached to this circuit A and B. In that case, that should be epsilon minus IR equivalent register. That also should be same as the potential increase out of battery. So in that case, current flow out of this gigantic register, equivalent to register, should be a potential increase divided by the register, equivalent to register REQ. So basically, this current from the number 2, same as the current from number 1. So if you just put them together, then they should be epsilon R1, R2, R3, same as epsilon R equivalent. So it cancel out, then you only see that equivalent total register out of this 3 registers, just combination of summation, the addition of these 3 registers. 3 registers. So that is the rule for the series connection. If the n number of registers connected in series, then total resistance is just sigma summation of all the individual resistors. Okay, that's basic rule. So again, if as long as the resistor they are connected in series, then total equivalent resistor out of a system is just a sigma summation and just individual resistors. Okay. Now there are also like different kinds of connection out of the multiple resistors. That is normally the second type of connection is the parallel connection. So if there are multiple resistors connected to the battery, but the current path split into the multiple sub-passes, then obviously you'll not be able to apply this analysis to drive the formula of the net resistors, right? So let me just give you another model, Bayesian model. So next one is resistance in parallel. So in the case that there are multiple resistors connected to the battery, but this time they are connected in parallel with the battery. So there are 3 different current passes. 1, 2, 3 to the resistor. Like this, there's R1, R2, R3, and you have the battery connected to the closed loop, plus to the minus. And the same thing, you have like a reference point A and B. Now, this condition or this circumstance is a little bit different from the series connection, because as I said, the current path split into the multiple passes. So one current goes to this direction. The main current coming from the battery, and there goes into goes to the first resistor I1, and the last current goes to the second pass, that is I2 plus I3, and second one goes to second resistor I2, the third one goes to the I3. Okay, so when the current comes back, then this current should be I2 plus I3, and that one should be, again, that's I, right? So there's 3 separate current passes connected to these three resistors, then you can actually convert this model into the simple one resistor model, the simplified version. So that if you just imagine there's big gigantic resistor connected to the battery, that resistor itself will represent three combination of three resistors. So that is R, EQ, and current goes here and goes here and goes here, right? And that is the bias with the battery. So this two model, they should be same. So we have find out the relationship between this net resistor and the individual resistors. So now, based on the Ohm's law, the current itself is the voltage divided by resistor. So I1 should be V over R1, and I2 is the same, V over R2. I3 is V over R3. Same for this model, simple model V. I'm sorry, that's I itself. This I is same as this I. Well, let me just change the color. This I should be this I right there, same I. So the I must be same as voltage drop divided by equivalent resistor. So as you can see, once the current comes off from the battery, then there goes one goes to the R1, next one goes to R2, third one goes to R3. So combination of these three current out of three resistor should be same as the current from battery. So from that, I should be equal to the I1 plus I2 plus I3, right? Now you plug this all three definition into this formula, then that should be V equals I equivalent resistor, same as V over R1 plus V over R2 plus V over R3. So here's the potential of system. They're all same for R1, R2, R3. So you can cancel V out of the this equation, both sides of this equation, and only leaves this relationship. So that 1 over the resistor of equivalent to circuit model is same as individual inverse of individual resistor. The combination of the individual inverse of the individual resistor like this. So that is a relationship for parallel connection. So if you have multiple resistor connected to the battery in parallel connection, then total resistor out of the system should be combination, summation of the inverse of the individual resistor. If you generalize this relationship in the more genetic case, then 1 over R equivalent resistor is sigma summation J is 1 to the N, 1 of R J. Okay, so you see the difference between the parallel connection and the series connection.
Wait, in the diagram for
Yeah.
the parallel,
Mhm.
why was it I2 plus I3? Isn't it also, don't you add I1 as well into
Okay, Hannah, what was the question again?
yeah, in the previous drawing that you did, it
Mhm.
said that it was in the whole like circuit, it's
Mhm.
I3,
Mhm.
but you didn't add like I1 into it, and I was just like curious like why I1 wasn't added there.
Okay, here. So let me redraw it. So this is R1, R2, and R3, right? The battery produces I, and I goes to here, and that goes to I1. This one is I2, and this one is I3, right? So
Yeah.
now I1 is flows into the R1. So if you look at the total amount of current after this junction, then only this I2 and I3 remained in this spot right there. I2 plus I3.
So if it like
Yeah.
so if it went inside like instead of resistor 1, it went to like resistor 2 instead, would it be like I1 plus I3?
I1, which one? This I2?
So if like the charge went into our like resistor 2 instead of resistor 1, would the total like I be I1 plus I3?
How can that possible that the current goes to the first resistor first?
Because I know for like capacitors, when we have like parallel capacitors, it could
Mhm.
choose like the charge could choose whether like it could go to capacitor 1, capacitor 2, or capacitor 3. So would it be like the same properties for like a resistor where it chooses which resistor to go into?
No, I mean this is I mean basically that's we just put the notation to only just label that current flow onto the each register. So whatever this amount of current goes through this register, we just label it as I1, I2, I3, right? So all of those three current must be same as the initial current from the battery, right? So that once you see that once this total current comes into this point, that some amount of current must flow into the R1, right?
Hmm.
That is I1. And whatever current, it doesn't have to be the actually I2 plus I3. You can think of this I prime, but I prime is I minus I1 because whatever remained current, which is I prime, should flows in the next, sub root. Then you can think of this as I double prime. Well, obviously there is I3, but is that some amount of current must flows into the R2.
Okay, that makes sense.
And then I the remained current after this two current pass should flow as a third pass with the R3. So there's like one. So like you have, let me just give you a number. Now we have 10. I don't know. We don't have to worry about the unit. I mean, just assume that the 10 of current goes into first pass of this parallel connection. And now assume that there's like a 2 goes to the R1. Then there's like 8 should goes to the next pass, right? And if there's like a 4 goes to the second register, then next one should be what? 4, right? So the current total amount of current split into the sub passes with the individual register, and they should combine back to the current flows into the battery. So that's 10, 2, 4, 4. So basically that's right after the first pass, with the R1 only is a remain. That is the amount of current goes to the second resistor and third resistor.
So after it goes through the third resistor, it will be the current will be 4, and then once
Yeah.
it goes to 2, it'll be 8, and then once it goes back from
Yeah.
1, it'll be 10. So then it's like a full circle.
Yes, that's the current like 4. Now it comes back to the combine with this current 4, and that should be 8 again here. And there's combined with the 2, and that becomes 10 again.
Okay, that makes sense.
Yeah. So current, total current, that is actually that's a good question actually. The total current and total charge must be conserved in the given system. Okay, that is basis of actually Kirchhoff rule. I will show you that the principle that actually very important. You have to actually use that formula, that principle to analyze the circuit. So total charge in the system must be conserved, the same as the conservation of current and conservation of the charge. Whatever charge, just put it into the system. The current flow should keep that same amount of charge over the subroutine, sub passes. All right.
Mhm.
So that's as I said, let me just rewrite it. So here, probably you already learned this one, but there's two different characteristic of basic element of a circuit, depending on how they actually connected. So let me rewrite it. So here, the series connection and the parallel connection. For resistor, total equivalent resistor is just addition of individual resistor in the system. But for parallel connection, the inverse of that, the resistor of equivalence system is same as the sigma summation of 1 of Rj. But the capacitor is opposite. That is one of equivalent capacitor. If you have multiple capacitor in the system, then it should be like this in series connection. Hold on. 1 of Cj. Parallel connection, total equivalent capacitor is just addition of individual capacitor in the given system. Okay, so the expression of equivalent parameter of resistor and capacitor is the opposite way in their expression. Okay, so you gotta need this expression of multiple elements in the way to analyze the circuit with the capacitor and the resistor mixed in later on. So just keep it in mind how they actually add it into their system to find out the total resistor and the total capacitor. All right. So next one, Kirchhoff's rules. It's actually most important rules for the DC circuit analysis before we actually diving into sample example problems in next session in next week. We have to actually just touch over this concept more details. So we need to understand how it works. Okay. So let me write it down. Kirchhoff rules. There are two basic rules to analyze this circuit, closed loop circuit with the circuit element. So first law, number one, is called the junction rule. Junction rule or node rule. So the total current, that's actually what I already mentioned to you, based on the conservation of the charge or conservation of current. So the first law of the Kirchhoff's rule is the junction rule. The total current that enters a junction must equal to the total current that leaves the junction. So if you just draw some configuration, now you have a junction. You have the one wire, it goes into the disjunction and split into the multiple passes. So the current, two currents, maybe you have some kind of like a circuit element right there. And then you have current goes into the disjunction A, and the current I2. And another current goes to that same junction is I3. And now you have another circuit element, maybe just the battery, could be battery. And that also produced the current in the third direction. And that battery produced potential, the VG. And that force current pass is connected to the junction 2. I'm just giving you some kind of example configuration of multi-pass current model. So now that also has circuit element R1, and that has current flows into that direction I1. So now you see that the two current comes into this junction A. Two current entered into the junction A, and two current leaves this junction A. So this Kirchhoff first rule or first law, junction rule, just telling you now the amount of total current enters this junction must just be same as the total current leaves that junction. Okay, so current, total current conserved. Why this is important? Because in order to analyze that the total amount of current in the closed loop, without this current conservation or charge conservation, you'll not be able to analyze the circuit elements, because without that, you'll not be able to actually just find out how much current actually get it into the system. If this is not valid, then there's some kind of leak current or just energy loss. So you must have this relationship, otherwise you'll not be able to solve the circuit problem. And the circuit basically just system will not be actually existing without this junction law or junction rule. So that's number one rule of the Kirchhoff rules. And the second one is about the potential change, potential difference, or potential actually variation in the given circuit element. So the second law is loop rule. The sum of the potential differences, positive or negative, that traverse and any closed loop in a circuit must be 0. So let me just rewrite it. Sum of the potential difference or differences, positive and negative, that traverse and any closed loop in a circuit must be 0. So now let me give you another example too to explain this idea. So you have closed loop. Now we have like a battery connected to the closed loop. No. And you have like, just like the example I show you, they have three, maybe a resistor connected to this battery. And you have two reference point. It's like, so now this one is A and B. And now we have also, this should be D. So that let's just assume there's four reference point, A, B, C, and the last one is D. So R1 produced a potential drop. So that is V1. And R2 produced also the potential decrease, V2. R3 produced V3. And the battery itself actually create the potential increase, potential rise. So within this closure loop, from the battery to the battery along this loop, you have certain amount of the potential increase or potential drop, but your net potential out of this closed system must be equal to 0. So that means you have V1, that is from the R1, and V2 from the R2, and V3 from the R3, and from the battery V4 should be equal to 0. So that means your net potential must be equal to 0. Okay. So the same as like charge conservation or current conservation, your potential change or potential variation produced by the circuit element must be conserved too. So that's actually a powerful tool because if you take into account that the potential variation produced by the circuit element, if you add them together, that should be always equal to 0. So you have to find out how much potential change by individual component, and that could be combined with the junction rule, first Kirchhoff rule, that you should be able to find that the individual values of resistor or current flow. So all the increase or decrease in the electrical potential energy, or for example, caused by the resistor in the direction of the current, must be balanced by all the increases in electrical potential energy. For example, like electrical, for example, caused by source of like this EMP or the battery from negative to the positive terminal. So simply speaking, if you're connecting this closed loop to the battery, this battery or the source of electromagnetic force itself always just increase the potential level. And the resistor, as long as your current pass, like your current pass is this way, right? As long as this current pass along this resistor is same direction of the loop, then this resistor is actually the knock down the potential level. So simply speaking, the way that battery works in terms of the potential variation is opposite to the resistor. So resistor lower, battery is increase the potential level. All right, as long as they are just the right direction, the same direction of the loop. You can choose the direction of a loop as you want. Okay, it doesn't have to be the one direction. If you want, you can actually have opposite direction, but you have to stay with the same convolution, same rule. You have to apply same rule to the individual circuit element. Okay, you don't want to mix up. So what I'm saying is, if you, for example, now if you just choose that the current path, I mean your loop of analysis is, for example, like counterclockwise. Now you see that the current path is opposite to this loop, right? So the loop, the direction is counterclockwise, but the current path is clockwise, right? In that case, the resistor itself raised the actual potential level, but this battery actually did knock down. So battery should comes with a minus sign, but the this resistor comes with the plus sign. So I will just give you some summary of this loop rule right now, so you have the better understanding. Next page. So number one, let's just summarize that the two rules. At first, junction rule. So the charge per unit time that goes into a junction must equal the charge per unit time, which is actually current, that comes out. So that is the same as law of conservation of charge. Okay. So that's charge conservation law. It's same as charge conservation law. And second, loop rule. Now, let's start with the register. So it's the number one register. Now you have like a register element. Oh, hold on. R, and current goes from left to the right. And now your loop of analysis, same direction, like this. The loop. So you see that the direction of the loop is same direction. Then, now the loop, the same as current, same direction. Then, the potential by this resistor, potential is dropped before and after, okay, by current times resistor, amount of the current times resistor. So the potential decrease by IR. Now, number two, if you have resistor R, you have the current flow I and R, but you set up the loop of your analysis in opposite direction with I mean, then along the resistor R, then loop direction of loop is opposite to the current path. It's the opposite direction. Then because of this, then you have actually increased the potential by amount of difference like I times R. So after the before and after, you potentially increase by this resistor by choosing that the loop direction of the loop is opposite direction of the current. So that potential increase by this IR. Okay, that's for resistor the common case. Now let's take a look at the battery. Number 3. Now you have like a battery connected to the wire. There's a closed loop like this, the plus and minus, and the current in this way. You choose that the loop that has same direction of current flow, so it's a loop. Then you have a battery itself has the potential V. Then that battery is increase the potential from 0 to the V. So if the loop is the same as the EMP or battery, then potential increase by V. Number 4, you have battery and the current flow in the left to right, and you choose that the direction of the loop in opposite direction, then the current flow. Then obviously, as I said before, your loop, you choose that opposite direction to the current of EMF or battery, then potential drops or potential decrease by V. So it comes with a negative sign in your analysis. Okay, so you have to memorize or have to remember this at least 4 ideas to analyze that the closed loop. So these 2 rules, junction rule and loop rule, as backbone of a circuit analysis. You have to apply exactly same way to analyze multiple paths the circuitry. So it helps you to actually find out the value of individual circuit element. Okay, we will have a much more better idea how to use these rules with the example problems in next session and next week. I'll get you some example problems and we can just walk through them with these basic rules and find a better idea how it works. All right. So any question? That is actually a main part for the DC circuit. The basic principle is pretty simple, but in order to have some feeling on how to use it, then you've got to solve a lot of problems too. So we will go through the multiple different problems from next session. Any questions?
No, I think everything makes sense. Yeah.
Okay, you don't have any question for today, right? Okay, now I'll see you next Tuesday. I bring up some exam problems and we can just solve them all together.
Okay, sounds
Okay, all right. I'll see you next week, man.